Okay, so now in this section, we're going to take a look at some applications, and we're going to put to use the material that we've studied so far in this course towards solving some practical real-life problems. So the first one we're going to look at involves what's called a closed system, or here it's referred to as a simplified economy. And there's three energy sectors, okay, coal, gas, and electric. And each of these sectors produces energy, but they also consume energy and have to purchase it. So some of the energy that they purchase is from within its own sector. Right? Coal will purchase energy, and some of the energy that coal purchases comes from the coal sector, but some of it also comes from the gas and electric sectors. So this table gives you some details about how this went down, particularly in 2021. This is just again, this is a made-up problem, but just to have something more concrete and tractable to consider. We're going to just look at energy that was produced and consumed in one single year that happens to be the previous year. Okay, so if you look at this one column at a time, it tells you one by one, it tells you how the energy from each sector was distributed. So the coal energy, so energy that was produced by the coal sector, 60% of it was purchased from within the coal sector again. But then that leaves 40% that was sold externally to the two other sectors, gas and electric. So and it looks like they each split it 50-50. So coal consumed 60% of its own energy, and the remaining 40% was split evenly between the gas and electric. If you look at the gas sector, well, the coal sector consumed 40% of its energy. The electric sector also consumed 40% of its energy, but then the remaining 20% of the energy was consumed internally by the gas sector itself. And then for the electric sector, you can see that half of the energy that the electric sector produced was consumed internally. And then the other 50% was divided evenly amongst the coal and gas sectors. Okay, so that's just gives you an idea how to interpret this table. What we're going to do is look for an equilibrium in some sense. So we're going to introduce another idea here, and here's some new notation just specifically designed for this problem. So the idea is that P sub C, so let's focus on the P sub C. That's the price that the coal sector is going to charge as a whole for all of the energy it produced in 2021. And then P sub G, well, that's the price that the gas sector is going to charge for the total sum of all the energy that it produced in 2021. And then same with the electric sector. It's going to have a similar notation. Okay, so what we want to know is what would these values have to be in order for all three of the sectors to perfectly break even? In other words, all of the revenue they generated from the energy they produced matches exactly their expenditures for all the energy they consumed. That's what we're looking for here. What would these prices have to be set to? Well, that's not an easy question to answer. There's a lot of already there's a lot of factors here. So the chances of stumbling upon a solution just by trial and error, that's not very likely. But what we can do is we can use linear algebra to solve this problem. So what we're going to do is we're going to just one by one, we're going to look at each sector, and we're going to write down a relationship that describes the fact or summarizes the fact that the revenue must match the expenditure. And we'll do that with one sector at a time. Okay, so let's start with coal. Let's write down on the left-hand side of the equation, we'll write down the expenditures, and then on the right-hand side, we'll write down the revenue, and then we'll get an equation by setting those two quantities equal. So let's break it down as follows. So coal is purchasing some energy from the coal sector, it's purchasing some energy from the gas sector, and it's purchasing some energy from the electric sector. The total prices, or let me put it this way, the price of each of those purchases, if you add them together, that's going to be the total expenditure for the coal industry. So let's start by writing down an expression that describes the total cost of the energy from the coal sector, purchased by the coal sector. Well, it purchased 60% of its own energy, so it's going to have to pay 60% of whatever the total price of all the energy produced by the coal sector is. And that's what this notation P sub C represents. So it's going to be 0.60 times P sub C. So that's this quantity in a sense, right? That's all the energy the cost of all the energy that the coal sector purchased from the coal sector. What about the gas sector? Well, it's going to purchase 40%, so 0.40 multiplied by the total price of all the energy produced by the gas sectors, which is P sub C. And then lastly, for the electric costs, we'll just go 0.25 multiplied by the total price for the electric sector. Okay, so that's the total expenditure now for the coal sector. We don't know what those three variables are, but if we did, we could plug them in here and we'd have the total costs, the total expenditures of the coal sector for energy. That's got to be equal to the total revenue. Well, what's the revenue? The revenue is the cost of all the energy produced by the coal sector by itself, right? So that's just, well, let's just put a P sub C here. Okay, so that's our first relationship. Now, what about the gas sector? Okay, so well, the gas sector purchased 20, we'll just copy the same approach. It purchased 20% of the energy produced by the coal sector. It produced 20% of the energy produced by the gas sector. These should have been G's, pardon me. And then 25% of the energy produced by the electric sector. And that's got to be equal to the total the total cost of the energy produced by the gas sector, because that's what its revenue is. So that's going to be equal to P sub G. So that takes care of the gas sector. And then I'll just erase these because that's not really relevant anymore. We were using these numbers for that second equation. And then for the third equation, well, what did the electric sector spend versus what did it generate in revenue? Well, in revenue, I'll just write down the right-hand side first because that's easy. So that was its total revenue. Its total expenditures, well, it's 20% of the cost of all the energy produced by the coal sector, plus 40% of the cost of all the energy produced by the gas sector, and then actually 50% of the cost of all the energy produced by the electric sector. So that's the system of linear equations that we want to solve. Be very careful here, though, because this is, something looks a little weird here. What do you normally have on the right-hand sides of the linear equations? Usually you just have the constant term, right? These are not fully simplified. Not all the like terms have been grouped. So the variable P sub C appears on the left-hand side and the right-hand side. And over here, the second equation, you got P sub G appearing on the left and the right-hand side. And then for the third equation, you've got P sub E appearing on the left and the right-hand side. So this should be simplified. And the way you can do that is just simply move everything over to the left-hand side. So for the first equation, you're going to subtract P sub C from both sides. And I'm going to take advantage of copy and paste here to do this more efficiently. But if we subtract P sub C from both sides of the equation, well, over here you're going to end up with 0.4 P sub C, and on the right-hand side you're going to end up with a 0. And then on the second equation, we're going to subtract P sub G from both sides of the equation. And, well, over here you're going to end up with negative 0. Oh, erase this addition as well. You're going to have minus 0.80 P sub G, and then you'll have a 0 over here, right? Because just to clarify, so for the first equation, if I subtract P sub C from both sides, well, on the right-hand side, P sub C minus P sub C is just 0. So that's where I got the 0. But on the left-hand side, if I go 0. I'm just going to group the terms all together. 0.60 P sub C. If I subtract P sub C, I'm going to have negative 0.4. That's where I'm getting that from. And then over here, I subtracted P sub G from this middle term, and that's why I ended up with negative 0.80 P sub G. Okay, on the last equation now, though, we'll subtract P sub E from both sides. So what's that going to result in? Well, if I subtract P sub E from the right-hand side, I'll just have a 0. If I subtract P sub E from the left-hand side, I'll subtract it from this term specifically. So I'm really just going to change the positive 0.5 P sub E to negative 0.5 P sub E. Okay, so, and you've probably already noticed before I even say it that this is going to be another one of those systems that's not the nicest to work with. We're not going to want to solve this by hand, right? But let's go a little bit further. Let's write down the augmented matrix at least. So if we write down the augmented matrix, our first column corresponds to the variable P sub C. Our second column corresponds to the variable P sub G. And then our third column corresponds to the variable P sub E. And then we'll have our constant column like we usually do. So I'll just write down the rest of the entries in this matrix. And now we're ready to solve this. By the way, you notice it's a homogeneous system. What solution does a homogeneous system always have? It always has the trivial solution. So in other words, we could satisfy all three of these equations by just setting P sub C, P sub G, and P sub E all equal to 0. In other words, this would be trivially satisfied if all of the sectors, I'll just erase this, if all the sectors produced absolutely no energy at all, then, well, then you could put whatever you wanted in this table and it would always be true, right? So that's not really a particularly interesting solution. So we're not looking for that solution. We're looking to see if there are other solutions. And from what we know about homogeneous systems, if there is a single other solution, then we know we're going to have a free variable, a parameter, and in fact, infinitely many solutions. But let's go ahead and go further. And like I said, this is a nasty system. There's decimals involved. We don't need to solve this by hand, right? This is where a calculator would come into play. So I'm going to use an online tool, the one I already showed you. I'm going to use that same tool to row reduce this matrix. So I'm doing it partially by hand and partially using software. But if you row reduce this matrix, you'll get the following. The first row will be 1, 0, negative 1.25. 0, of course, on the right-hand side. The constant terms will always be 0. And then the second row is going to be 0, 1, negative 0.625, 0. And then 0, 0, 0, and 0. Okay, so we will need to set up a parameter, right? We've got two basic variables in the first column and the second column, because there's leading ones in those columns. There's two pivot columns. And then in the third column, there's no leading one, so that is not a pivot column. So the third variable, which is P sub E, is going to be assigned a parameter. So let's do that now. So we'll let P sub E be a parameter. Let's call it S. And then what's going to happen? Well, for the other two variables, we'll have to write down the equations that correspond to the pivot rows. So the second equation is going to give us P sub G is equal to 0.625 times S. And the first equation is going to give us P sub C is equal to 1.25 times S. I'm encouraging you to pause the video and do this carefully, right? Write out this equation. What are you going to get? You're going to get P sub G minus 0.65 P sub E is equal to 0. Solve that for P sub G and plug in your parameter. Same thing over here, right? You're going to end up with P sub C minus 1.25 P sub E is equal to 0. Solve that for P sub E, solve that for P sub C and plug in your parameter. And you'll see that this is what you get. And this allows you to put together the final solution. So but right away, you notice there's a parameter, right? So this is an example of what's called an underdetermined system. In other words, there's not enough information given in this problem to fully pin down exactly what these variables must be equal to. So one of them is allowed to vary. In particular, the energy produced by the electric sector, that's a free variable. So that can vary and be anything. But as soon as you decide what amount of energy is going to be produced by the electric sector, then that's going to immediately determine how much energy is produced by the other two sectors. But let's write down our general solution using mathematical notation as we normally do. I'm just going to write P as a solution vector here, and just the very next line just tells you what that means. It's just the vector consisting of P sub C, P sub G, and P sub E. So this is equal to what? It's going to be 1.25s, 0.625s, and then P sub E was actually equal to S. And that is, normally we would just say where S in the reals is arbitrary. But I'm going to actually back up, so don't write that down just yet. I'm going to back up. What's the extra restriction? Well, could we have S equal to negative $10? No, by nature, by the way these variables were introduced, these prices must be positive, right? Nobody's paying another sector to take their energy away. That's not realistic. But so we need S to be positive, and as long as S is positive, then the other two prices will be positive as well. So that just to keep things sensible, let's back up and mention that where S greater than 0, and let's go greater than or equal to 0 is arbitrary. So if S were equal to 0, then P sub E, P sub G, and P sub C would all be equal to 0. All of the prices would be equal to 0, and all of these sectors would be charging exactly nothing for all of their energy, right? So, or in other words, that must mean they're producing no energy, and that's not an interesting solution, but it is technically a solution. So let's put a box around that, and we'll call that problem solved. So that's a problem that had more than one solution, and our answer encapsulates that. So by the way, and just to reiterate too, the work in between here, I did skip some work, right, to row reduce this matrix to this matrix. I just used that same website that I showed you in section 1.3, the matrix.reshish.com. You're welcome to use that tool or any other tool to follow along. A lot of calculators can solve these systems as well.